Before we start the presentation, we'd like to thank the CBzinho of Lorena and the Xbox team of Unisal for taking its respective scores, questioning the viability and application on the drone. So then we could define the research fronts. The project. To explain our project to you, we will approach each research front and then synthesize all the components the drone must have. The drone supporting system. As a starting point, we need an innovation to solve the low atmosphere of Mars, which would require twice as many motors to provide the necessary drag, the utilization of a balloon, like an airship, built in 2 layers. For the inside coating of the airship, we have polyisopropane, because it has an excellent elasticity, resistant and abrasion. But its lifespan is low when exposed to the atmosphere agents, like solar light, UV, and oxygen. So for the external coating, it's decided we are using Kevlar 29. The extreme cold on Mars surface, was the main reason for the use of this material. Kevlar 29 resists temperature low as -192 degrees Celsius, with minimum damage. It also has low thermal conductivity and dilation, giving it a greater insulation. The Kevlar 29 also has great density and braking strength, which makes the drone able to sustain considerable force, keeping the weight relatively low.
The inside coating system, the internal layer of the balloon, would be made of polymeric latex. This would be produced by a bioreactor with genetically engineered Escola. The cells of this modified organism would be capable of converting glucose into polyisoprene, as you can see on the picture. This is a very attractive alternative to obtain this compound, once the other paths would require the use of fossil fuels or tree growth, impracticable on Mars.
The supporting function principle. The balloon is used to lift only the useful load, meaning everything sums up to the UAV with its components, with the required mass of gas to lift this extra weight. In a form to calculate the floatability made by the balloon addition on the drone structure, was necessary the atmospheric density of Mars calculus. The calculus are shown below. The mass structure is really inferior when compared to the useful load. That's why it was disconsidered on the calculation. In this way, the volume of the balloon depends on the useful load of the drone, which varies with the mission. Once the mass of the drone is exclusively supported by the motors, we deducted that the UAV is capable of making any material transportation. Well, now we have the system components. In the heart of the drone, we have the flight controller that receives powers from the battery. This power cannot be directly input on the controller. That's why we have a BEC to control the exact quantity of power that it receives. The BEC is also responsible for controlling the TDP and current of the power that is sent to the transmitter and the receptor. We have another problem that we encountered when building the drone was that the motors, when paired with the ESCs, there was too much interference from the electronic parts of the ESC. That's why we opted for an opto-ESC. This opto-ESC works by sending light signals instead of using a wired connection. This wireless connection between the ESC and the controller was opted because it can minimize the interference caused by the motors. Another motive for the ESC choice is its energy controller, which makes it turn off automatically with tensions lower than 3.2 volts and has a possibility of reverting the rotation. Now we have the voltage converter. The setup a ferrite converter with high resistivity and low energy loss, stable permeability through time, and low operative temperature. The flight controller. This is the Metex Systems Betaflight F405. Having a black box. Having a black box with micro SD storage, allowing the identification of programming errors, driving and possible interferences on the control system. This board also has an OCD that could help during flight, providing detailed information on the battery system interconnected on the supply. Now the remote exploration and data transfer. As requested by COBRUF to keep a viable communication in a minimal distance of 1,000 meters and control in wet and sand environments, we choose to work with frequencies higher than 30 megahertz. That's because this would allow the upload of videos and files and also the continuous communication between the drone and the base. Given that, we decided to use the component DigiXB Pro SX-RF, considering that it's widely used by specialists, and also for working as a transmitter and receptor simultaneously. According to our researches and technical file of the components we have, the data exchange with a maximum range of 14,500 meters at a 250 kilobytes per second rate, which makes transmitting data in a continuous and instant rate. This is the XB Pro SX-RF.
Well, about the landscape mapping, Mars, differently from Earth, doesn't have the aid of airships or satellites, and because of that, it is interesting the utilization of a drone for the study of the landscape and the field of Martian terrain. This technique consists of the utilization of a drone with a camera which hovers through a terrain, taking pictures of the place with a predetermined frequency. The terrain must contain certain reference points, which will be later used with quite an accuracy to determine the distance which the drone traveled through.
One of the requirements of COBRUF was the ability of the drone to identify gases such as methane in the atmosphere of Mars. In this way, we thought of a biosensor that could, when using bacteria, count the amount of methane present in the analyzed site. The biosensor would be made in microscale to occupy as little space as possible in the drone and interfere minimally in the weight. The idea was to create a small chamber with a permeable membrane as the wrap, where we could put bacteria in a medium with oxygen. However, this bacteria could only metabolize the oxygen if they came in contact with the methane gas. Thus, we would do an indirect measurement. We would measure the amount of maintained in the atmosphere from the consumption of oxygen by the bacteria coupled on the drone. Another concern our team had was on the maintenance of a space station in Mars. The Martian soil is rich in perchlorate, which is prejudicial to the growth of crops that are essential to maintaining life in another planet. Thinking about this matter, we found an interesting project called Ecolonizer that uses synthetic biology pathways to degrade perchlorate using little water resources. Some bacteria are naturally capable of degrading this compound, such as the Chloromonas aromatica, but it's more applicable to use an engineered E. coli once it has a more predictable behavior. On this project, an E. coli DH5-alpha strain was used to clone and express genes from the aromatica, capable of degrading perchlorate. The degradation system would be using a bioreactor. The drone would be used to help on the transportation of contaminated soil samples to this reactor, and then to take along the treated soil for the environment. The reactor would consist in 5 compartments. Compartment A is the compartment where it begins the reduction of perchlorate, followed by a component B, in which perchlorate is taken to be reduced. After the soil decontamination, the water remaining from the process is taken to a desalination tank, which is marked as component C. Component C, which is an optional setting, contains cyanobacteria that secrete simple sugars. This extra reactor can be used to supply glucose to E. coli in the main reactor. These sugars are sent to compartment E, in which they are mixed with other components in order to form culture medium for the E. coli cells, which are gradually sent to main reactor. In that sense, the whole bioreactor is self-sustainable and capable of generating products essential for the use on the space station, such as water and decontaminated soil for planting.
Well, as a conclusion, the challenge made by the competition to develop a totally theoretical drone to fly over Mars was not even close an easy job. It was difficult to obtain data about the red planet, information about drones, especially the definition about the motor and propeller, and simulators that offer the options to change variables such as air density and atmospheric pressure. We decided to go after an alternative to get the drone up in the air. We found that we could use a balloon, like a Zeppelin, but with nitrogen as a fuel, because it can be found in the atmosphere of Mars. Now, considering the base knowledge of the team and for being new in the field, we decided to explore something we could have a better development. This way, we have made a partnership with CBC, the Synthetic Biological Club, what allowed us to have a great development in the field of sensing by biological factors. Another successful partnership was with XBots, who helped us with some electro and electronic simulation components and circuits. Now, about some future work. The main point to be observed in the future elaboration of these projects is analyze if it is really viable the application of a drone, considering the difficulties posed by Mars' work environment, like the barely existent atmosphere, which makes it difficult to keep the drone flying. Another job to think about in this project is a more elaborated study about the conditions presented by Mars to gather data to simulate possible missions. This way, it is possible to obtain a more sophisticated definition about the motors, the propellers, and the battery to be used in the drone, also considering the addition of photovoltaic scheme in the balloon to raise the autonomy of the airship.
The presentation was finished. Thank you.
Sim, Congratulations for your work. It's an amazing project, very interdisciplinary. I have some questions. One of the main challenges of Mars robotics is dealing with Mars dust or regolith. What will be the effect of Mars dust in your drone design and operations?
Just a minute. Okay. Can we answer in Portuguese?
Yes, you can.
Thank you. He answers better.
Obrigado. Boa tarde. Um dos principais motivos que a gente colocou o balão como conceito no projeto foi a dificuldade em Marte, por conta de lá ter uma atmosfera muito baixa, se comparada com o que nós temos no planeta Terra. Esse problema em si dificulta muito por conta que as hélices em si elas criam uma diferença de pressão. Por essa diferença de pressão ser muito baixa, no caso de Marte, a gente teria dificuldades para fazer a suspensão do drone em si. Então, uma das soluções é fazer esse balão com a base com nitrogênio, por conta da atmosfera de Marte, no caso, ser composta por CO2.
Thank you very much. Apart from Mars, where do you believe are other great opportunities for drones on solar system exploration?
Do sistema solar.
Eu não diria exatamente o planeta, mas no caso dos estudos que são feitos das luas de Júpiter. Seria o mais enquadrado assim em características para se ter a utilização de drones, devido tanto às atmosferas encontradas em outros planetas, quanto também à gravidade em cada um.
Thank you. Another great challenge on dealing with Mars exploration is the radiation. Did you take radiation into account in your studies? What do you have in mind about it?
Sim, foi levado em conta a radiação no nosso projeto, considerando principalmente o material que a gente pegou para utilizar no balão, que no caso o material...
O Kevlar 29, ele é resistente a UV e radiação, por isso seria o revestimento externo do balão.
Que até um dos fatores que o material que seria o do revestimento interno teria problemas por conta dessa radiação. Então, justamente, a gente teria esse revestimento como Kevlar.
Thank you. And what was the most difficult topic you faced during the project?
Eu acho que um dos tópicos mais difíceis foi definir em si o motor a ser utilizado, por conta que, querendo ou não, a gente ainda tem que fazer toda a parte de movimentação do drone e definir um motor, sendo que todas as especificações são tidas no planeta Terra. As variáveis obtidas para fazer esses cálculos não tem muito relacionado a drone, é mais sobre navios ou se não aviões. Então, os coeficientes a serem calculados, é bem difícil encontrar uma teoria em si específica sobre a parte de drones. Então, acho que essa foi uma das maiores dificuldades para a gente abordar no projeto.
Thank you. Congratulations for your amazing job. We would like to know if you want to say a few words before we finish.
Again, we would like to thank the CBZIM of USP and the Xbox team of Lorena. Thank you very much.
And thank you all for listening to us today. Thank you.